Okay, so picking up where we left off in the last video, we're going to solve this second example of a linear homogeneous recurrence relation. And we're going to start the exact same way, where we get all the terms to one side. So subtract this term and add this term. And then we're going to form that same characteristic. So this term is 1t squared minus 4t plus 4, which gives us, again, a quadratic that we can factor. Okay, so what we get in this case is we get a repeated solution. So really, we probably wouldn't write that solution twice, right? We'd just say we have one repeated solution. Okay, and in this case, when we have one repeated solution, our solution to the recurrence relation is going to look a little bit different. So remember, before we had some constant times this number to the n plus another constant, and in the last example we had this number to the n, but we can't just write 2 to the n again, because really what we've done is we've just taken 2 to the n and added 2 to the n, right? We've just kind of added the same thing twice. So we have to make this term be a little bit different. In the last example, we had a 2 to the n and a 3 to the n, so they were already different. We don't want to repeat this term, so what we do is we just stick an n in here, so that these guys aren't the same. It's 2 to the n times a constant and n 2 to the n. It's 2 to the n. n 2 to the n times a constant. Okay, so this is the general form of the solution. Now I'm going to go apply my initial conditions. If I put 0 in for n, that's going to make this term go away because I'm plugging 0 in for n. 0 should go in for n here. Right, but when I multiply by 0, this is just going to go away. And I get to set this equal to 1. So just focusing in on this equation, again, multiply by 0, that's all going to go away. So really what I'm left with is just that b times 1 equals 1. So that gave me the value of b right off the bat. So I'm going to go ahead and put that back into my solution. 1 times 2 to the n, so that's just 2 to the n. Okay, put that back into my solution, and now I'm going to apply this condition. Plug 1 in for n. And I get to set that equal to 1 as well, and that gives me a nice equation I can solve for d. So that's just 2 plus 2 times d equal to 1. And I'm going to subtract 2 from both sides. 1 take away 2 is minus 1. And that gives me then that d is minus 1/2. Okay, so here was my solution. The only thing I didn't know there was d, and now I know that d is minus 1/2. So I've got 2 to the n, so plus minus 1/2, so I'll just write that as minus 1/2 n times 2 to the n. Okay, and I would take that as the answer. You could take this a little bit further using the rules of exponents. 1/2 is the same as 2 to the minus 1. And so I could combine this guy and this guy using the rules of exponents. The base is the same, so I can add the exponents. So we could write that as 2 to the n minus n times 2 to the n minus 1. We could do that, and that would be fine, but I think once you find the constants, you can write your answer with those constants, and that's perfectly fine. So this would be perfectly acceptable. And so those are our two examples. Those are the two cases that we'll see. One where you get two different solutions to your characteristic, and the other case is where you get two repeated, or I guess I should say one repeated solution to the characteristic.